While a variety of methods are available for analyzing engineering risks, event trees have become commonplace for dam and levee safety studies, because through event trees, you can take a complex process, like a dam or levee breach, and deconstruct it into a series of events or steps that are easier to specifically define and to evaluate. This helps us with analysis and understanding the risk. It also helps us in communicating the risk and aids the decision-making process by making the key factors more evident. Like all other tools, event trees are imperfect, and their potential value depends on the skills of the user. So hopefully we will all be skilled in developing and understanding event trees at the end of this module. First, some definitions. An event tree is a sequence of random variables or event sets that can be associated with random variables. It is a graphical depiction of the sequence of events leading to a particular set of outcomes, which in our case is typically breach or non-breach, which have associated life loss and economic consequences. A chance node is a branching point at which a new variable is introduced in the tree, and a branch probability is the probability of the event given the occurrence of those events that precede it in the tree. I will step through an example of an event tree on the next slide. Here is an example of an event tree. Each branching point of the event tree is referred to as a chance node. Branches and their associated branch probabilities emanate from each of the chance nodes. In the last node at the rightmost side of the event tree are end nodes, which are aptly named because that's where the tree ends. An event tree pathway goes from node to node along the branches until you reach an end node or outcome. Generally, as discussed previously, we're going to use separate event trees for each initiating event type, flood and earthquake. For simplicity, even though they are not, we will almost always assume them to be mutually exclusive. This way we can keep them separate and can simply add the probabilities to get the total failure probability. Although flood and earthquakes are not mutually exclusive, the odds of having an earthquake at the same time as a large flood event are low and typically negligible. Branches in event trees can represent a variety of things. It can be the system response of a dam or levee system to event sequences, human actions and interventions, emergency response and factors affecting survival during flooding, or continuously operating or standby systems. Starting first with the basics of event trees. Each branch represents an event or state of nature. Each pathway of an event tree is unique. An event sequence must be logical, but not necessarily chronological. Branches must be mutually exclusive and collectively exhaustive. Remember that mutually exclusive events cannot occur together, and the probability of collectively exhaustive events will sum to 1. Event tree branches are conditional on all prior pathway events. These are the events that are to the left in the tree, as shown on the next slide. The probability of D is conditional on the occurrence of events A, B, and C. Next, we have some rules. Event tree rule number 1 is pretty basic. All probabilities must be greater than or equal to 0 and less than or equal to 1. Event tree rule number 2. The sum of the probabilities originating from a single chance node must be equal to 1. Here, the sum of the probabilities from these 3 branches must sum to 1, and each set of branches emanating from each of these 3 chance nodes must also equal 1. Events must be mutually exclusive so they can be summed, and because they must sum to 1, they must also be collectively exhaustive. Event tree rule number 3. The probabilities for each branch must be conditional on all preceding branches. In this example, we start with the probability of reaching a given stage, then the probability of hydraulic fracture given the stage, followed by the probability of initiation given the stage and that hydraulic fracture has occurred. So the branch probabilities are evaluated, conditional on all preceding branches being true. This is a very important rule to follow, else the total probability for a given event tree pathway will be underestimated. Event tree rule number 4. The probabilities for a branch can be a function of any state variable in the preceding branches. In this example, failure is a function of both stage and discharge. Perhaps we are looking at a dam conduit where the outflow is large enough to overtop the training walls, and that leads to erosion and slope instability. Then the only way for slope instability to result in a breach is for the pool to be up and the slide to be large enough to lower the dam crest below the pool. So failure in that instance would be a function of both stage and discharge. Finally, some calculations. Probabilities along pathways are multiplied, and probabilities across branches are summed. In this example, to get the probability of cracking, there are two pathways that result in cracking. In the event tree, we start with an earthquake, and the foundation either liquefies or does not. If the foundation does not liquefy, there can still be enough movement to crack the embankment. If the foundation does liquefy, the probability of embankment cracking is even greater because of the increased differential settlement. The sum of these two end probabilities will then give the total probability of cracking. Event tree analysis steps. Regardless of what software package you use to complete your calculations, whether that be RMC QRA Calcs, RMC Total Risk, Palisades Precision Tree, or DAMRay, these steps will hold true. With the exception of Precision Tree, which can be cumbersome to use for big projects, it can be difficult to see how the event tree math is being completed, so you need to know where things are going and how the inputs are being used. We will discuss this more in future modules of the course. Regarding the steps, you'll first want to make sure all your input data is organized. Figure out your risk-driving failure modes, how you are going to evaluate them, and the loading variables for which they are dependent. These loading variables can be inflow, stage, overtopping depth, PGA, or something else. Determine your consequence types in your consequence centers and the significant exposure factors. I'll talk about exposure a little more later. Determine your breach scenarios to estimate your consequences. Then when you go to create your event tree or trees, depending on your project, start with the loading variables and any factors that affect them, like gate reliability or debris blockage. From that loading, proceed to the potential failure modes. Each will have their own sub-event tree. Then on to exposure factors and consequences. Once you have your tree mapped out, input the estimated loading probability relationships, your system response probability relationships, state functions, exposure factors, and consequences. Be sure to have someone double check your inputs because there's a lot going on and it's easy to type a value in wrong or paste something into the wrong place. In the end, when you have completed the calculations and get some results, be sure to do a gut check to make sure the results look reasonable and make sense with your inputs. It's also good practice to perform a sensitivity on all key inputs to help you understand and ultimately communicate what is driving the risk and why, and how those risks could change if your uncertain inputs change. This figure shows the general framework for building a project event tree. Again, the loading feeds into the system response, which then leads into the associated consequences. You can also use sub-event trees for any step along the way. Let's walk through an example event tree. This example project event tree uses all the different functions that can be used in an event tree analysis. The function or variable types are continuous, discrete, transform, system response, exposure, and consequences. Using the following slides, we will step through the different function types and discuss their common applications in risk analysis. Please note that event trees can sometimes become very large. While the risk calculations for the entire event tree need to be completed to arrive at the final risk estimate, the portrayal of the event tree can be condensed using collapsed nodes, which are indicated in the tree by plus signs. When a plus sign appears in the tree, it signifies that structure of the event tree will be identical to the branch above it. In this example, the 1 gate inoperable and 2 gates inoperable contain plus signs. Therefore, the structure of the tree after those nodes is identical to the 0 gate inoperable branch. Each gate scenario, however, results in a different peak spillway discharge, peak stage, and peak overtopping depth, which are obtained using the transform functions. The first level in the example project event tree represents a continuous function. Continuous functions are denoted by a fan symbol and represent continuous random variables that can take on an infinite number of values over a specified range. In practice, we represent continuous functions using a series of branches, like the one shown in the box to the right. How many branches you need will depend on the project conditions, the potential failure modes you are evaluating, and how precise an estimate you need. In this example, each branch represents a range of reservoir elevations, and each is assigned a corresponding probability. Together, these branches are both mutually exclusive and collectively exhaustive, and they cover the entire range of the flood hazard. Continuous functions are most often used to represent hazard variables, such as peak flood stage, stage duration, spillway inflow or outflow, or earthquake ground accelerations. Level 2 is a discrete function. Discrete functions are used to represent discrete random variables that can take on a finite number of values, with each value being represented by a separate branch. The number of branches is selected to match the number of discrete values that the variable can take on, with each discrete branch being assigned a probability of occurrence. In this example, the discrete random variable is Tainer gate inoperability for a spillway containing 2 Tainer gates. As such, 3 discrete function branches are required: 0 gates inoperable, 1 gate inoperable, or 2 gates inoperable. As with the continuous function, the probabilities of the discrete function branches emanating from a single discrete variable must sum to 1, making them mutually exclusive and collectively exhaustive. In level 3, we have transform functions. As their name implies, transform functions are used to transform values of one variable to another variable. We can use set relationships that can help us transition from one variable to another, like inflow to outflow, inflow to stage, or stage to overtopping depth. Performance and associated consequences can be functions of different loading variables than what was used to define the initial hazard function. Most of the time, they are a function of stage, but they can be a function of a lot of other things too, such as overtopping depth or inflow. So being able to use a transform function to move from one variable to the next is very useful. You may have noticed that there is a node at the front of the transform branch, but no nodes between the transform and system response function branches in the next level. The tree is formatted this way to allow for the transform variables to be aligned with their corresponding system response functions. From a mathematical standpoint, the transform function is treated as a dummy branch that has no significance as an event in the event tree, and it is assigned a branch probability of 1 to neutralize its effect on the computed probabilities. As a result, the sum product of the transform functions and their corresponding system response functions is equal to 1, and is therefore collectively exhaustive as required by event tree rule number 2. On this slide is a more detailed illustration of how a transform function works. Here, the continuous hazard function is a function of stage, and the system response is a function of overtopping depth, which do not match. Because they do not match, we need a state function to relate stage to overtopping depth. The state function in this case will be the stage minus the top of dam elevation. This, of course, gives us the overtopping depth. So now we have a relationship that transforms a continuous loading relationship to one with the same variable as our system response. We now know the probability of each specific depth of overtopping, and we have the system response as a function of overtopping. So we can then multiply those across each loading range and then sum them to get the probability of failure. In the next level of the event tree is the system response functions. This is where we will input the estimated system response probabilities, which are the probability of failure given the loading. Like I said before, the system response can be a function of a variety of things like stage, PGA, earthquake magnitude, etc. Each set of system response functions will have a corresponding function for no failure. This is the case because each set of branches from a given node must be collectively exhaustive so that we satisfy event tree rule number 2. System response probabilities are often calculated using sub-event trees. You can do the calculations in one large event tree without using sub-event trees if you want, but the trees will get quite large and can be very difficult to manage. Using sub-event trees will help you to organize and manage the overall project event tree. Here's an example of a basic internal erosion event tree, which most have probably seen. It moves through flaw, initiation, continuation, progression, unsuccessful intervention, and breach. Here's another example of a sub-event tree that splits seismic crest deformation and overtopping by whether foundation liquefaction occurs. You can also have a sub-event tree within a sub-event tree, like for intervention. Remember, we had unsuccessful intervention back on the internal erosion sub-event tree. Exposure functions are the fraction of time that a portion of the population at risk is exposed to dam or levee failure in a particular way. At a minimum, we consider time of day since most people are usually in different places during the day than they are at night. At night, they are usually at home, whereas during the day, they are typically at work. Other examples might be weekdays versus weekends. Time of year can sometimes also be important, like if there's a popular camping area that will have more people there in the summer, or if there's a ski resort that has more people in the winter. How many exposure branches you need to account for is going to depend on how the population at risk changes at different times, days, or seasons. Last, we have the consequence functions: breach and non-breach life loss, and economic cost. Just like system response probabilities, consequences can be a function of peak stage or discharge. When calculating dam or levee risk, use incremental consequences for the failure pathways. When calculating residual risk, use breach consequences for the failure pathways. Non-breach consequences will always be used for non-failure pathways.